The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. It is 12:01 now, so we will get started. My name is Anna Zylik. I'm with ICF, and we are the vendor working on behalf of Eversource and Energize Connecticut to bring these passive house trainings to all of you. So thanks for joining us today for this Passive House 201. We are recording this training and we will make it available afterwards. And these trainings are at no cost thanks to Eversource, a proud sponsor of Energize Connecticut, and also in partnership with Connecticut Passive House. A quick reminder that this webinar is eligible for AIA CEUs, specifically one AIA HSW. Also, don't forget that we are also offering a 50% cost reimbursement for professionals pursuing either FIAS or fee accreditation trainings. So this includes the cost of the training and the exam. And once you become certified, we'll work with you to process the 50% cost reimbursement. So our email address is down below on the slide. Feel free to reach out if you do have any questions. You will receive a follow-up email after the webinar today that will include a link to a survey, and we would really appreciate you filling out the survey with any feedback that you can provide us on today's session. Luke, can you go to the next slide, please? Thank you. Also, a reminder that we have another Passive House webinar coming up, the Path to Certification. It's scheduled for Wednesday, June 9th at noon with John Morsher. So make sure you are registered for that one as well. And with that, I will pass it over to Mark, who's also with ICF, to share the new building incentives.
Hey everybody, welcome and thanks for joining. Mark Pignatelli, I'm a senior manager with ICF, and just wanted to highlight the new Passive House incentives for multifamily buildings with 5 units or more that was recently announced by Eversource for Connecticut. So the next slide will just touch on some of the incentive levels. So certainly something to be aware of. There's some contact information down below the chart here. But essentially, there's some pre-construction incentives for projects looking to pursue Passive House certification, feasibility study, modeling, and then also a post-construction incentive around the certification costs. So you can see the chart here. I won't read through all this, but we definitely want to make sure everyone in attendance today is aware of this great offer. So really excited to see how things start to progress in Connecticut now that there are some really lucrative incentives here to help offset some of the incremental costs or some of those soft costs up front as folks start to get together with projects teams and do some early planning and designing. So certainly reach out to the contact info below or to any of us. We'll have some contact information towards the end as well. And yeah, so we will be monitoring the chat if there are questions. And with that, I think I can hand this over to Luke at this point.
Thank you. And actually, I'm just seeing that I have the incorrect slide deck up. So I'm going to quickly transition over to the correct slide deck, if I may. Sure. Apologies for that.
Yeah, and while Luke is just switching over slides, we're as Anna mentioned, we have an upcoming training in June. We will be offering trainings throughout the rest of the year. We have a couple other trainings in development for a little bit later, towards the end of the summer, beginning of the fall. So, this is really kind of that lunch and learn style, 1 to 2 hour trainings that we offer. We also do offer more technical building science workshops, which can be 3 to 4 hours long. So certainly be on the lookout for future trainings. We're going to be continually offering these well into next year. So thanks again for joining. And Luke, it looks like we're back on track here. So back to you.
Yes, indeed. Sorry, I had 2 sets up and just picked the wrong one. So thank you everyone for joining our Passive House 201 on the technical aspects of Passive House. I am Luke McNeely. I'm a registered architect in Massachusetts, also a lead AP and a certified Passive House consultant. And I work with Mark and Anna at ICF as an account manager for high-rise, multifamily, and Passive House projects, helping to manage the incentives for those. I just wanted to clarify, this is an introductory course. It is still rudimentary knowledge about Passive House design considerations. It assumes that you've got some awareness of Passive House, and Passive House Connecticut recently did a PH2 or 101. This is not some formal training under FIAS or PHI, although it is available for AIA credits. For those interested in why Passive House work but aren't yet engaged in a certification course or project, this is a good intro. We'll be covering some basic massing and shading, air barrier and weather barrier and thermal layers, information about ventilation, heating and cooling and hot water systems, and some of the modeling that we use to guide the Passive House process. The big picture here, I won't spend too long on the learning objectives, but we are learning more about Passive House, how Passive House can help us achieve net zero energy or net zero carbon, and understand our building enclosure as the key to making it work, and how the mechanical systems play into that. So why Passive House? Is this just a fad like so many others? What is it about Passive House that is attracting your attention, for instance? And what is it that has attracted the attention of larger industry groups and the utilities and sponsors? Well, it's in large part because it is a focus on fundamental principles of building physics. So really, this is using basic building science to reduce energy loads where they occur. And that is an excellent way to make progress on energy savings. So you've likely heard a lot about net zero energy. Hopefully you've heard a bit about Passive House. And what is the difference? Well, net zero energy does not specifically require a reduction in energy load at the building. And so as long as you are offsetting the amount of the load with renewable energy, that can be considered a net zero energy building. Certain standards may have some requirements, but technically a large fossil fuel energy use could be offset by renewable energy. And so Passive House is a different approach to that, does not get into renewable energy directly, and is really more about reducing the primary energy load of the building before adding renewable energy. And this does result in significant greenhouse gas emission reductions and makes the building ready for net zero energy, and even possible to achieve source positive energy. And so really, we do see Passive House as a means to achieve net zero energy very effectively. So Passive House does come in a couple different flavors. There is the Passive House Institute US, or FIAS, and they have 3 different current standards. The FIAS Plus Core 2018 has been the version that has been active, and they've recently introduced FIAS Plus 2021, and each of those has a different source energy limit based on kilowatt hours per person occupant per year, and that has gotten tighter. And with FIAS Plus 2021, it has now opened up kind of a variable depending on the project's location, its climate, the size of the project, and the occupant count in the building. PHI, or the international version of Passive House, has 3 flavors as well. They're Classic, Plus, and Premium, with increasingly stringent EUI, or energy use intensity, in kBTU per square foot per year. FIAS, the US version of Passive House, utilizes a program called WWOOFI, developed by the Fraunhofer Institute, which dynamically looks at the climate and a variety of other things, and I'll describe that a little bit more later, in order to test the conditions for your building specific to the climate in your area. Similarly, the PHPP, or Passive House Planning Package from the International Passive House Institute, does a similar job, just in a spreadsheet format. Passive House is complementary to a lot of other building standards, including Energy Star and Living Building Challenge, also very effective with LEED as a energy component and an indoor air quality component to those standards. But Passive House often comes across as being kind of about the latest gadgets, and just want to be very clear that Passive House is not about products or technologies, although those are useful elements within a Passive House. There certainly are requirements about efficiency of systems and efficiency of assemblies, but it is not the assemblies and equipment that make a Passive House a Passive House. Passive House instead is really more a whole building systems analysis, looking at the energy flow through the building, taking into account the climate of the building that the building is within, and the context, such as shading and other buildings that may impact it, the massing and shape of the building and its envelope, how that's all enclosed, and of course the mechanical, electrical, and plumbing systems that go into that. So this is a common diagram, and while it is focused on a single family house, it is applicable to multifamily as well. Just trying to wrap up a number of the key factors of the Passive House approach. And starting over at the lower left, we have our high performance glazing systems. So they can certainly be operable, but to have a high quality, low U value, high air resistance, so no leakage, and an excellent lack of thermal bridging in the frame. Optimizing the window to wall areas for appropriate allowance of sunlight into the building, and shading to help block out unwanted heat gain during the summer. Throughout the building, we are looking for thermal bridge-free construction and an air barrier that really contains the interior conditioned space to avoid any draft. Also, of course, we have super insulation to provide a continuous thermal envelope, and to put all of this together, we have mechanical systems that provide the fresh air that is required, extract stale air from where it needs to be extracted, and ideally capture as much of the energy that has been put into the interior conditioned air as possible before that is exhausted. And some of the kind of simplified but important distinctions between conventional building as we have known it over the past decades and the Passive House approach. And here I say it's versus a little bit, but it is true that conventional building has been considerably leakier. We have moderate levels of insulation. Cold air can leak in through cracks and gaps. Typically, air infiltration is a significant part of poor performance in existing buildings. And windows that tend to lose heat through radiation as well as air leakage. And this does lead to warm air being able to escape, moist air being able to move through assemblies, and for a convection loop to be developed that leads to a discomfort as well as radiative losses through colder surfaces like lower performing windows, versus the passive house approach with super insulation and a consistent air barrier to reduce drafts and to reduce that striation of temperature gradient within a space. High performing windows, so there is no radiative loss through the window. And again, a mechanical ventilation system to maintain a comfortable level of airflow, leading to a much more comfortable space overall, as well as a higher performing space. Of course, there are impacts directly on the users and tenants and additional benefits. We do end up with a healthier indoor air quality that is draft-free and comfortable. Surface temperatures are kept well above dew point to reduce mold risk. And pairing that with low VOC, low toxin materials and filtered fresh air, we can end up with a much better indoor environment. In addition, of course, Passive House has certain other qualities such as passive survivability or resilience is the popular term now, in large part because temperature changes during extreme weather conditions are muted within the space of a passive house. Temperature drift is much slower, so even when systems are shut down or during power outages, the spaces can be livable for longer. So there are longer and slower heating and cooling loss times. Another added benefit is the insulation does also minimize the amount of noise transfer. So when we're doing a passive house analysis, we are really looking at the total gains from solar energy through the windows and heat through the assemblies, interior occupant heat, equipment energy losses within the envelope inside the building, as well as the outputs and efficiencies of those equipment, and then any renewable energy system inputs that may be present if that's planned, versus the overall losses in energy through infiltration and leakage and through general heat transfer or moisture transfer through assemblies and components, and of course through the ventilation systems. So Passive House really does look at independent locations, and we use TMY3 weather data, 30-year averaged, to get a general sense of the weather characteristics of a particular building. And that gets put into the modeling system so that we have a baseline of performance that the building does need to address. So we've got all of the temperature, wind, moisture, precipitation, etc., and orientation associated with that. And so as we get started with a project analysis, we really do look at the building's overall massing, the amount of area of envelope to the volume of interior conditioned area, and its orientation on the site. Of course, we want to know how much of the envelope has window area and where that window area is located. And then, of course, also how it is impacted around by its context. Are there trees on site? Are there other tall buildings nearby? Are there solar shades going to be integrated? Or are those recommendations that could be provided to enhance the design? This diagram that comes from Pembina and Fias kind of illustrates many of the systems that go into the accounting of what makes a passive house work. And for the moment, we're going to focus on the envelope, which is highlighted here. The key elements are highlighted. And so really to dive in, of course, the enclosure or our envelope is the key to all of this. With a good envelope, we can control how energy is flowing through our building. And so the envelope plays a number of different roles. Largely, air management has been discovered to be a huge player in the energy performance of buildings. Leakier buildings lose a ton of energy through moisture-laden and heat-laden air. And so controlling that airflow really makes a big difference. Heat, of course, we manage through insulation, and as code has recognized, continuous insulation does that better than cavity insulation. And so combinations of that, or ideally fully continuous insulation, makes a big difference. Water management on the exterior, really controlling bulk water from precipitation events is another key role. And then vapor management has been another element that has really come to the fore as we understand that things happen, assemblies do get wet, moisture, relative humidity on one side of an assembly versus another changes regularly, and there is a pressure between them that does drive moisture into and through an assembly. And having the ability for the assembly to breathe in terms of its moisture content is important, and making sure that we have a path for that moisture to get out of the assembly is important. And we analyze that as we put together the model of our particular project, building examples of the types of walls or components that we will be using and assigning those to our building components, for which we can then see how air tightness, moisture content, and thermal layers all play roles. Similarly, we do the same thing for our windows, looking specifically at the function of the glazing U values, but also the frame U values and the total installed U value of those windows. And so we can test again multiple window types against each other, fixed, operable, different manufacturers, etc. As I mentioned, air leakage is a real critical element of this, and while Fias and PHI do have slightly different standards, they are comparable. PHI utilizes the air changes per hour at 50 pascals, and 0.6 air changes has been a well-known and well-recognized minimum requirement for them, and that it has been broadly recognized throughout the industry. Fias looks at things in cubic feet per minute of air change at 75 pascals per square foot of the envelope. And that is, again, comparable to the 0.6 air changes, but it allows for a bit more flexibility in terms of the scope and scale of the project. So it definitely addresses the different types of projects that are out there, whether they be tight boxes or very spread out components, with different requirements for larger buildings of greater than 5 stories, and specific compartmentalization requirements for dwelling units as well. And just as a comparison, the Army Corps of Engineers has roughly 3 times the level of air leakage allowable as the FIAS and PHI requirements. So it's very important as a project is being designed that we look at how an air barrier really is put together. And the Passive House consultants that work on projects typically will dive into the weeds on this and work with the design team and ownership team to figure out the logistics of the sequence and application of the air barrier, how it is being installed, who will be responsible for that. For that is all a critical part of success in Passive House. And of course, in the meantime, you also get a good look at how the thermal barrier is working for insulation continuity. And so we are looking at thermal bridging and how to mitigate that. And speaking of thermal bridges, what is a thermal bridge? Well, it is really wherever you have a conduit for heat to pass through an assembly. And so thermal bridges are very common at structural interfaces, columns and beams that touch the facade, slab and floor edges that meet the facade as well, and of course around frames of windows and doors. All of these areas are structural components that are often difficult or have been typically uninsulated and need some attention to avoid letting the heat flow from the interior to the exterior. Of course, wherever you have cantilevers or penetrations, we have special conditions that need attention. And that's not all. We also have anchors for our curtain walls and rain screens whenever we have masonry, for instance, but also roof drains, waste pipes, and wherever, again, we have penetrations for electrical or mechanical. All of these need careful attention. And while it might not seem like much, it does add up. As you go around a whole building, there are many instances that will be thermal bridges, and they need to be thoughtfully addressed in order to not end up sinking a project. This is a study that Stephen Winters Associates did, and even after a lot of effort on the part of reducing thermal bridges, the thermal bridges were still 6% of the total heat loss through their envelope, and so contributing a significant amount of the heat loss on the project. Thermal bridges can be point or can be perimeter type linear thermal bridges that go for long distances. And all of those need to be entered and calculated in the Passive House modeling. Of course, good detailing really does matter. And this kind of gets back to the concept of massing. Here are 2 parapet examples, both continuously insulated, for example, but with a significant difference in simplifying the insulation path to avoid essentially radiator type fin situations where a parapet extends up and out of the heated area. This is a common kind of situation and a challenge to detail and implement well, but certainly doable. Similarly, on the far right here, we have a typical steel angle off of a floor plate to support a brick ledge, uh, versus three alternative approaches on the left, a steel knife plate versus a proprietary system versus just a hollow stainless steel section, supporting a smaller brick ledge, brick angle out past the insulation, resulting in significant differences in the performance of that wall system. Thermal bridges can happen anywhere that we have structural components. And so it is always important to take the time and to have the expertise come together to help go through where we might find these thermal bridges and think about how they can be addressed. Again, commonly at floor plates and structural intersections where we cannot have continuous insulation on the interior, we'll typically find these. And very commonly, of course, at the window, sill and header conditions and jamb conditions. And so one of the key solutions to addressing thermal bridges is to provide a continuous layer of insulation. This can be challenging to accomplish at times, and depending on the scale of the building, the modeling may show that a significant amount of exterior insulation is required. So detailing the connections for that insulation is an important part of the discussion. But it is common, especially in the larger multifamily projects now, that we can work with modest amounts of continuous insulation, like 2 inches of a rigid type insulation can often work, depending on the effectiveness of the total project and other systems. Of course, the same goes for all aspects of the envelope, including the roof, and where the roof and walls meet is always a challenge. One of the other common challenges that we see in the multifamily project area is when we have residential construction over a parking garage or other unconditioned space. And then we typically see a few different common solutions associated with that, but each with their own challenges. And so whether it be something like a spray foam tight against the underside of the floor sheathing and wrapping some of that structure, or insulation above the floor sheathing to provide an interior layer of continuous insulation, or something that is really hung below everything and encloses both the structure and any systems within that. Again, each has kind of its own flavor of challenges and benefits, and so it's always something that needs to kind of be looked at on a project by project basis and a cost basis to really understand what is the best fit. So how are we doing? We are halfway through. We're actually flying along. I was worried because we have a lot of slides here. But Mark and Anna, I think if we are willing to have a little break for questions, now is not a bad time, but I would say at most just a 5-minute moment. What do you think about that?
Sure, yeah. I'm not seeing any questions come through the chat yet. So I know attendees are on mute otherwise. So if folks do have questions, feel free to put them right into the chat. It might get a little clunky if we try to unmute folks. So I think Luke, maybe you could just keep rolling, and then as questions pop up, maybe we try
Sounds
to
good.
take them at the end. We should have a little bit of time.
Excellent. So yeah, I just wanted to make sure, since we're transitioning now from the envelope into the systems approach, I thought this might be a good moment. So we are now going to dive into energy recovery, ventilation, and HVAC with a particular focus on moisture control, of course, because that is one of again, the key drivers of energy and durability as well. So on the mechanical side of things, we do typically see three basic kind of categories of decision for the different system types. For ventilation, we have our energy recovery ventilators and heat recovery ventilators. Heating and cooling, of course, and domestic hot water. Each of those can be set up to be a central type system that is individual units, individual components of equipment covering an entire building or large zone of a building, versus a semi-central type system, which might be floor by floor or wing by wing type systems, versus ultimately the unit-based individual systems addressing each living residential unit. So it is always kind of a mix as to what is going to be the best case for a given project. Often this does have to do with the ownership's interest in metering for the tenants, whether this is something in which the tenants are on the hook to pay all utilities, or if there is some assistance, or if there is some other plan in terms of addressing utilities within the rent in some respect, or just having them covered. And so this is, again, another layer, but the key for the passive house approach is ultimately its total efficiency. And so regardless of the system approach, it is that system's efficiency as a whole, not just the piece of equipment that is being installed, but also its piping and plumbing and distribution approaches are all considered. So here's an example, for instance, of a centralized type heating and cooling system. We have a chiller and a gas-fired set of boilers that are being pumped throughout a building. As a common multifamily type approach, perhaps most often used in the low-income construction space, where tenants often have heat included in their as a part of the system, versus the more independent unit-based type systems. In this case, indoor units for air source heat pumps, and an outdoor unit, which you can see just up here on the outside face of this building, feeding a wall unit on one floor and a ducted unit on another floor. So that's a common approach to kind of the more individual unit-based type systems for heating and cooling. And then similar to the air source heat pump, there is the VRF, or the variable refrigerant flow type systems, which use the same wall units and ducted heat pump indoor units, but use a single centralized outdoor condensing unit in order to control all of the interior units at once. Then there is, of course, a complicated switching and management system to be able to send refrigerant to where it is needed at the temperature that it is needed. So one side of a building can be getting cooling while another side could be getting heating, or one unit could be heating while another unit is cooling. In both the VRF and the air source heat pump cases, there are some considerations in terms of the performance and the ducting and design. Using the wall units, of course, we've got minimal ductwork, and using the individual unit-based type systems, indoor systems, we can limit ductwork to an individual unit as opposed to throughout a building. And there are heat recovery options through integrating an ERV into the space, where we can get considerable energy improvement within a given unit. Of course, one of the other considerations is there may be a lot of refrigerant piping in these systems that needs to run throughout a building, and so that is perhaps an added cost to the concept. The wall units are great. They don't require any additional ceiling space, but they do require power at each unit. And sometimes the loads in a passive house, as in the heating and cooling loads, can be very small and perhaps smaller than the units that are available can provide. That's been improving over time, but you can end up with oversized units in a very small, efficient apartment. The ducted units are great in that they can be hidden, much more aesthetically pleasing, but they do require additional ceiling space and, of course, a certain amount of ductwork that all needs to be sealed. Again, this is true of both the VRF and independent air source heat pump versions. And then we get into the ventilation. So heating and cooling a residential unit is something that we have separated in the passive house building science world from the ventilation. And that's partly because we can address the efficiency of each system better, and we can make sure that the needs of each concern are addressed more specifically. So if you need heat, that's great, you can have heat. You will always need ventilation, whether you need heat or cooling or not. And so the ventilation is typically kept as a separate approach and is typically a continuous, balanced extraction and intake of fresh air. So we're exhausting our stale air from places that generate air that does need to be exhausted, such as our kitchens and bathrooms, whereas we are bringing in fresh filtered air to our living spaces, like bedrooms and living rooms. And we can do that all with heat and energy recovery. There are a variety of different HRV and ERV equipment out there. This is a cross-flow type system that is commonly used at the apartment level. It has generally a low efficiency, and is at that low efficiency is not commonly seen as ideal for passive house level performance. Very often our ERV is a critical part of a passing design for passive house certification. And so these simple cross-flow type ERVs don't always quite get there. But the concept here is good and illustrated in that, for instance, if we have warm, moist air outside on a summer day, and we are busily cooling and dehumidifying the interior air, we don't want to give away all of that effort by exhausting our cool, dry air and bringing in warm, moist air. And the ERV core helps us transfer the heat and the moisture to the outgoing stream. And it's important to note that the streams themselves do not cross-contaminate. They are side by side in counterflowing paths. And so the air does not mix, but the heat and the moisture can move. A more efficient version of that same concept is the counterflow, and as you can see, it's just basically an extended version of that crossflow type core, and it gives basically the air more time to transfer that energy across the two paths. The commonly pardon me, I hope you're not hearing too much background noise, but I do have some going on at the moment. But commonly found, we do have the wheel type energy wheel. These scroll type systems can be very efficient, are typically used on the larger scale multifamily projects. You find them up on the roof, and with good filtration, they can provide excellent quality, excellent indoor air quality, safe and effective energy recovery. Again, as with the heating and cooling systems, we can do centralized or decentralized type systems. Centralized, perhaps covering a number of apartments or floors or the whole building, versus the unit by unit type. And of course, there are benefits in design and constructability for each of those. And I won't list them all, but essentially, we certainly do see benefits in the centralized systems in terms of fewer wall penetrations, but are challenged because we have more vertical shafts and perhaps more horizontal distribution, floor-to-floor height requirements, and of course more ductwork that needs to be sealed and fire rated with dampers. Whereas for the decentralized unit by unit type approach, we don't have to go through the floors, but we do have to go through the walls. And so there are 2 penetrations per apartment that need to be carefully air sealed, and a certain amount of ductwork within the apartment that needs to be coordinated. It is also a benefit to maintenance and operation to have a simpler centralized type system with fewer units to maintain that is certainly more accessible to the maintenance staff. But of course, that also does put the cost of ventilation on the owner with a centralized system. Whereas with the decentralized systems, the power is all on the tenant's panel, so that can be considered a bonus, but filters need to be changed every 3 months, and access to these louvers should be maintained and considered because maintenance will be required at some point. Transitioning over to domestic hot water, of course, this is drinking, food prep, sanitation, hygiene. We're not talking about swimming pools or commercial cooking on this. But one of the interesting things is we find that domestic hot water often becomes the major load in passive house buildings after heating and cooling has been addressed and ventilation has been addressed through excellent envelope detailing and development, and high performance heating and cooling and ventilation systems. So in the study of a high-rise in New York City that Stephen Winters did, for example, you can see here heating and cooling energy amounts to 11% of the total energy usage of this project, whereas domestic hot water takes up a full 30% practically. I won't get into plug loads, which obviously are the lion's share over there. That is based on a standard that Passive House uses for all plug loads, regardless of occupant, for residential plug loads. And so that is simply occupant based, and that is a calculation. This study, as you can see, you might consider lighting and heating and cooling all together as roughly 25% of total energy use, versus again our domestic hot water being still more significant than all of that. And so how do we deal with our domestic hot water? Similarly, we've got our central type systems that do have benefits in terms of reduced pumping power. Efficient gas boilers are allowed and certainly do play a big role at the moment, with often a consideration that they may be switched over to heat pumps in the future. In all of these cases, utilizing a demand control type recirculation loop can really help to reduce energy losses in a loop. And I won't get into demand controlled, but demand control is an excellent way to not have continuous pumping and continuous waste of heat in a domestic hot water loop. In other words, it only turns on when there is demand. One of the challenges, of course, of the central systems is loss of floor space. And of course, again, it is on the owner's meter, and so not a tenant-based type system. Semi-central, as an alternative to that, is now available on the heat pump, in the heat pump world, but could also be addressed on a natural gas basis. And it has many of the same benefits, including it can help migrate over towards beneficial electrification of buildings, and again, can use the demand control to help further reduce losses. These types of heat pump condensing systems do require roof area and similarly are on an owner's meter, but they are available and in the market now. As an alternative on the decentralized systems, gas-fired units are not allowed in Passive House within residential spaces. And so the alternative really is electric storage or heat pump type systems or instantaneous electric, but I won't get into that. But here are two different heat pump type systems that would be on a tenant's meter, and again, easily meet the Passive House criteria and are heat pump, so very efficient type systems. They do require a maintenance closet, and the hybrid type units like the Ream that you see in gray requires venting as well. A split type system like the white one from Sandon does require outdoor area for that outdoor condensing unit, but the indoor storage tank does not require any special venting. All of that, of course, needs to be input into a Passive House model. And so systems specific efficiencies, their distributions, the piping, the insulation of the piping, et cetera, all have to be addressed in the Passive House model. And ultimately, we are able to pull all of that together into a Passive House report that helps us see where do we fall relative to the targets that have been set for this specific project? Do we meet the heating and cooling demand? Do we meet the load over the course of the load might be the instantaneous load for the worst case day? And do we meet the source energy? You can see in this report, I have a project that does not meet its source energy and I get a big red X. And that's again on a kilowatt hours per person per year approach. And so we use that as our guidepost, and ultimately that report needs to be sent off to FIAS or PHI in order to demonstrate that a project is indeed passing, along with all of the project documentation that directly supports the inputs for this model. Lastly, I'm going to go through our construction phase support, in which third-party verification needs to be provided. Ideally, that is engaged during the design process so that a verification team can understand the drawings and can comment on it prior to construction. The third-party verifiers are responsible for enforcing the passive house aspects of the design during construction and really do need to have some authority through the owner and the architect to be able to help the team meet these goals. And really that is critical to the success of passive house performance and its certification. Many of these components, if they are not done properly, can lead to trouble down the road in terms of moisture issues, mold issues, etc. And so verification is a quality control approach. We do that through testing of assemblies like blower door testing, air leakage testing, looking into the insulation connections and continuous insulation, verifying that things have been done according to the spec and drawings, and documenting any issues during constructions and suggesting good solutions. Of course, documenting to the construction team what is allowed is an important thing. So when you're going for an airtight building, for instance, you want to be sure that all of the trades and the subs know that they shouldn't be cutting through airtight membranes just to stick something wherever they think is most convenient. And so everything does need to be reported to a supervisor who knows what's going on in terms of the passive house approach.
Hey, Luke, just to jump in real quick, sorry to interrupt. We're
Sure.
getting up on time here in a couple minutes, and we do have some questions. Do you have
Great.
do you have a few
Yes.
slides to get through, or?
No, I'm done. I just wanted to say blower door testing, and forgive me, I was looking at a timer that said 50 minutes, so forgive me, I was giving myself more time than I
No
expected
problem.
there.
No.
I will simply say that blower door testing is something that should be done at a midpoint and then at a final level. The midpoint is critical in order to get a good sense of where things are. And then the final is, of course, the final, at which point you won't have a whole lot of opportunity to make corrections if it's not there. And I will simply skip over to say that this not only can be done, but it is actively being done at large scale all over. And so with that, thank you. And happy to jump into questions.
Yeah, Luke, great job. A lot of content to get through in a short time. And I know we are pretty much at the hour now, but if folks are able to hang on for a few extra minutes, we can get through a couple questions. And actually, I missed a few that did come in the queue when we had that moment, but I was able to answer a few. And there are a couple here that I'll throw your way, Luke.
Sure.
So one question here, let me scroll down, is what process would you recommend to develop data about cost, schedule, potential carbon reductions to help projects determine if Passive House is right to achieve their goals? First thing that comes to mind for me is a feasibility study. Luke, anything more to add there?
So getting a feasibility study from a certified passive house consultant to look at your design early on in the design is really a key approach that we have found to be effective. It is important to have a team that is aligned with the goal of achieving passive house, and starting that process early on really helps the whole development team and design team understand what is required to meet the passive house criteria and what will that cost. And so in a feasibility, you can easily test these design issues and start to understand, okay, we do need triple paned glazing, or we do need shading, or we do need continuous insulation, and what will that cost? Then the design team can put that out for pricing. Ideally, that again happens early in the schematic design level so that you don't get too far down the design path and have thermal bridges and other issues that need to be addressed but are more complicated to deal with.
Great. Let's see here. Another question around thermal barriers being so critical. Do you think that simpler elevations are part of the answer, with texture, material changes, and color becoming better choices for aesthetic expression versus three-dimensional complexity? Good question.
Yeah, that's a great question. So any project can ultimately find a way to address all of the thermal bridging and air sealing requirements. It's just a question of how complicated is that process, how much will it cost to do it. Certainly on development team's first passive house project, I'd recommend keeping things simple, because simple certainly is easier to succeed with. And as a team gets a handle on what these requirements are and how flexible certain elements are, it becomes easier to expand on that on subsequent projects. Certainly, we have seen teams that have taken on complex massing and assemblies. But the better prepared that team is, the more successful they are. So simple is a recommendation, certainly, to get started.
Great. A couple more here. We'll keep rolling. It looks like we still have folks on the line, which is awesome. Appreciate you guys hanging in a little bit longer. So let's see. How often do the filters need to be changed on an ERV, HRV?
So a common recommendation is every 3 months. You could say every 4 months. Some people can make it work for 6 months, but it would be manufacturers, follow your manufacturer's recommendations on that. It does depend on the particular system, again, whether it's individual unit based or central type systems. And that, again, is all something that needs to be kind of considered as you're making these decisions about what's the best system for your project.
Couple questions around heat pump water heaters. One, can they work with dehumidification systems, and are they effective in larger homes?
Heat pump hot water systems certainly are effective in the individual unit level. Ventilation of those systems is a consideration. They do bring in ambient air and they blow out cold dehumidified air because they're pulling heat from the heat and moisture of the air that passes through. And so we do see that in multifamily projects, perhaps putting a utility closet at the corridor so that the air can be extracted from the corridor and exhausted back into the corridor, where a corridor ventilation, heating, and cooling system can deal with all of that, versus having that in the unit, in which case the tenant may feel, may hear noise and may feel the ventilation of that heat pump unit, versus the larger scale commercial heat pump units that are now available. Some of the real large heat pump manufacturers are also putting together heat pump to heat exchanger type systems, and will be coming out in the U.S. with some heat pump to hot water type systems. Although at the moment there are more domestic systems available.
Great, thanks, Luke. Yeah, and I'll try to hit two more questions before
Sure.
we wrap here. In one of the first slides, you indicated net zero with on-site renewables might still contribute to carbon pollution. Why is that?
And that was simply because a net zero that does not address energy consumption at the source, the load of the building still needs so much energy to perform. And if that project is not energy efficient, then it needs a lot of energy, and that energy is going to come from the grid. It might come from a generator. It might come from whatever the grid mix is. And an inefficient building will simply require more of that. And so that does lead to more greenhouse gas emissions. Passive house as an alternative restricts the amount of energy that a building requires, and therefore it restricts the amount of greenhouse gas first and foremost, and then the renewable energy is just covering that smaller load, the smaller need.
And just one final question here. You showed one slide earlier, Luke, where you missed the source energy target. I think it was one of the examples you shared. Is it possible where you can make that up by adding site PV?
Yes. So Passive House does allow PV to help you with the source energy requirement. And so if that's the only target that you are missing, it can help. However, there are limits in place on Passive House. You can't, again, have a hog of a building and just make it up with PV. So there is still a minimum performance level that is required before you're allowed to use PV to make up the difference.
Great. Yeah, so hopefully we're able to hit on most all the questions. I did notice there was another question around how to identify local passive house consultants, professionals in your area. I would suggest checking out the FIAS or FEE websites. I believe they do have like a search directory of sorts where you can try to identify. And then, if you do have any questions, any general questions about the presentation or about future trainings or about the reimbursements to become a Passive House professional that we touched on earlier, we have our email address down here at the bottom, passivehousetrainingct@icf.com. Happy to take any follow-up questions via that email address. You can also see Luke's email is he graciously listed it there as well. But yeah, we really appreciate the time. Thanks for hanging on an extra 10 minutes here to get through some of the Q&A. So yeah, be on the lookout. Definitely sign up for the Connecticut Passive House newsletter. They do a great job in partnership with us to promote these trainings. So you can sign up for their newsletter. But yeah, thanks again for the time, Luke. Great job. Appreciate it. There's a lot of information here. Passive House has really started to take off, certainly around Massachusetts, Connecticut, and we're starting to see some uptick, just in New England in general. So we're really excited to bring these trainings and really look to transform the market here to not only just exceed the energy codes, but go even deeper and look to try to hit these Passive House certifications. So with that, thanks again for joining. Thanks, Luke, and we'll hope to see you soon. Have a great day.
Thank you, Mark, and thank you, everybody.
Cheers.
Bye.